Today we're going to explore the fourth and final contest in ACSL Elementary Division, which is graph theory. So first of all, we need to define a graph. A graph is a collection of vertices and edges, and an edge is the connection between two vertices. So all the vertices you can see here are A, B, C, D, and E. Those are all vertices. They're points. They will most likely always be labeled. And as you can see, the lines in between of them, those are the edges. Like over here, this is edge AE, this is edge AD. So all these lines you can see here, those are edges. So basically what graph theory is, it's the mathematical theory behind graphs like these and their features and all the applications and how they can be used in real life. So first of all, we need to figure out how would you actually write your answers even if you figure it out. So the notation, if you ever need to notate anything where it like a cycle, traversal, Hamiltonian circuit, path, etc., these are a lot of types of paths that you will need to identify, which we will talk about in a little bit. But basically you need to write it in a form of a list of vertices. For example, in the graph below that you can see, the highlighted part, if you start from vertex A, is written A, B, C, D, because it's going from A to B, then B to C, then C to D. So now let's get started with some terminology. So first of all, path, path length, simple path, they're all sort of the same thing. So a path is just a list of vertices that are connected by edges. In the previous slide, when I showed you A, B, C, D, it was a path. The path length is how many edges there are in the vertex, in the path, sorry. So basically this is 1, A to B, and then B to C is 2, and then C to D is 3. So the path ABCD is of path length 3. And this path is also a simple path because none of the vertices in it are repeated twice. A comes once, then it goes to B, then C, then D, and then none of the other vertices are repeated. So this is a simple path of path length 3. The degree of a vertex, this is a property of a vertex, which is how many edges are coming into a vertex. So basically we can look at vertex A, for example. We just see how many edges are coming into it. So there's one coming in straight from E, there's one coming from D, and there's one coming from B. There's no connection from A to C, so that is not one of the edges. So basically this A has degree 3. The vertex A has degree 3. This is used in traversals, so it's important that you know how to do this because they're used a lot in traversals. So a traversal, now let's move on to that, is a path that visits every edge exactly once in a graph. We'll learn how to find it in a bit, but basically what it's saying is you cannot start somewhere and then go double back along the same path. You need to visit every single edge once, and it's a path, but it's not a simple one because most likely there will be vertices that have to be repeated for every edge to be covered. So this is possible. As you can see, we just make this diamond shape and then go all the way out to E, and it's not repeating any single edge twice. So now let's move on to cycles. So cycles are paths that start and end at the same vertex. and it has to be more than length 2. You can't have a cycle written A, B, and back to A, because that's only length 2, and that is, you're not allowed to double back on the same exact edge twice. So that is not a proper cycle. So basically a cycle, you could probably spot one right away. So it can start from any vertex here in this diamond and just go along the path, and this is a cycle because it'll start and end at the same vertex and none of the edges are repeating. But you also have to remember this, that if you're listing a lot of cycles and you go one that goes A, B, C, D, A, B, C, D, A, you'll always have to write the starting vertex twice. So you cannot make another one B, C, D, A, B, because that is the literal same thing. But one thing is, you can go make it go the opposite way and say A, D, C, B, A. You can make it go the opposite way because that's a new cycle, but you cannot just reposition the order vertexes in the same cycle, because the cycle will always keep looping around. So now let's do something pretty interesting, Hamiltonian circuits. So a Hamiltonian circuit is a cycle that visits each vertex exactly once. So basically it's a cycle, so it has to start at one vertex. So let's say it starts at vertex E. Now, vertex E is the starting point. It can go to vertex E again, but when it ends, because it's a cycle, so E has to go to A, and it is impossible to get one in this graph because to get back to E, you will need to pass through A again. So you cannot, and you can't repeat A, so it's actually possible though, because it's actually impossible because you can, in this graph, because this E is just hanging there, and if you start with it, then you have to go to A directly, and then to get back to E you will have to pass through A again, which makes it impossible. And any other path would make you always repeat the A, because you would be unable to go back to the starting vertex after reaching E, because you would have to pass through A again. Now, this is another concept called connectivity. It's pretty simple actually. Basically, it's saying, is there a path between any two pairs of vertexes? Basically, are all the vertices connected? And this is actually pretty simple to see, but you have to know the actual vocabulary term. So say this edge AE was not there, then it would not have connectivity, thus would be a disconnected graph, because this vertex E is just hanging there on its own, and since this AE edge does not exist, there's no path from any of these vertexes to vertex E. So that graph would be called disconnected. Now let's move on to some types of graphs. So connected/disconnected, we just did this. If a connected graph is a graph that has a path between any two pairs of vertices. You can pick any, they should all be connected. If this isn't true, then the graph is called a disconnected graph. And now this is another interesting one. A null graph is a graph with no edges. So this is actually pretty simple. There's literally no connections. It's just like all these points, A, B, and C, they're just lying there. There's no edges whatsoever. So that's just a null graph because none of the edges are connected by anything. And now this is number 1 called a complete graph. So a complete graph is a graph where there is an edge between every single pair of vertices. So basically that's pretty simple. They just have to be connected with everything. And now traversable graphs. So a graph is traversable if there is 0 or 2 angles with odd degrees in the graph. So remember, degrees are the amount of edges that are coming into the vertex. So if there's 0 with odd degree, then the traversal just starts from any vertex, doesn't really matter. But if there are 2, it will start from one of them and end to the other. So if there's a traversal possible, then the graph is called traversable. Now here we can I'll sort of show you how all those things look. So first of all, the connected graph. So E has to have a connection with every single another connection with every single vertex other than A, which already does. So there would be a connection like this. A just needs a connection with C. B needs a connection with D, since we already made one with E, right? And D does not need any more connections because all the connections have already been made. So now these 1, 2, 3, 4, 5 edges, when added, make it a complete graph. Now let's start with traversals. So basically we just have to see first what are the degrees of each angle. So vertex B, we can see it's only connected to A and C, so its degree is 2. Vertex A is connected to B, D, and E, so this is 3. E is only connected to A, that's 1. D is also connected to 2, and C is also connected to 2, which are D, B, C, and A respectively. So now, since this says 1 on it, and this has 3, so our traversal has to start with A and end with E, or start with E and end with A. It's pretty simple now. If you look, you need to start, if you say you're starting from A, you need to start from A and then get back to A while passing through every edge so that you can connect to E. So you just make this loop because that's the only way you can connect to A again, and then you just go to E. So the traversal there's multiple traversals possible. You can go in any direction. You can start with E and then make the loop, either way. So the one we just did would be written as A, D, C, B, A, E. Notice A is repeated twice, but that does not matter. We are only looking at what edges are repeated, and none are. It only visits each one once. So now let's move on to some practice problems. And these are taken from past ACSL tests. So this will give you an idea of how it will be like on the actual tests. So, question number 1. Given the following description, list all of the edges represented using the first letter of each person's name. Do not include any duplicates. And then it says all of these names which are shaking hands. So basically, we just have to pay attention, make sure we do not duplicate anything. So it says Amy first, so start with A, and then A, D, and A, E. So those are 2. And now we have to be careful. We're done with the ones that start with A. And now E, it's saying EA, but we've already done AE, so we need to make sure we do not do the duplicate. And now EBE. I'm just doing alphabetical order. So now we're done with the ones that say Eli. Now B, it says Ben shakes hands with Eli, but we've already done BE, so we just skip to BC and BD. And now DA, we've already done that. DB, we've already done that, so we just need DC or CD. And now CB and CD, we've already done those, so there's just these 6 edges, AD, AE, BE, BC, BD, and CD. So this is actually a pretty simple type of question. You just need to make sure that you pay attention and do not duplicate any edges. Another problem, so this one is about a complete graph, and it's saying list them in alphabetical order. So again, pay attention to this. It says AB, not BA. You might just get deducted a point if you write it the wrong way, so just pay attention. So now we just did something like this. So which vertices start with A is A not connected to? So A is there's 4 other edges other than A. It's connected to 3 of them, so it needs AC. AC needs to be there. Now C is only connected to 2. Now C is only connected to 2, B and D, and we already made a connection with A, so all it needs is CE. A connection with E, so that it's connected with every other vertex. Now let's move on to B. B has a connection with C, E, and A, so all we need is a connection with D, so BD. And now let's go to D. D already we just added a connection with B. It's already connected to A and C, so all we need is DE. And we already have 2 connections of E now, which were required to make it a complete graph, so we do not need to add any more. So this is the answer: AC, CE, BD, and DE. Now another question. If you're delivering pizza from location Q to all other places and returning to location Q when you're finished, how many different routes could you take? So basically this is the number of Hamiltonian circuits that start with vertex Q. So there's actually a pretty simple way to do this. So you know it's going to start with Q. And now you can go to any vertex. Let's just go to R first. So now QR, and R can go to 2 other vertexes. So that means there will be 2 with QR. And now we do QR, one will go to P and one will go to T. And now if it's gone to T, then the only other connection other than going back to Q already is S. It has to go to S first, and then P, and then go back to Q. And over here, if it goes to P directly from R, then it'll have to go to S, and then T, and then go back, and then come back to Q. So there's 2 with that start with R, and now let's go QP. P can go to S or R, so there will again be 2 options, QPS and QPR. Now if it goes to S, then it has to go TRQ. You can just sort of eyeball this mostly. And now if it goes to R, then it goes T. If it goes QPR, then it goes TSQ. And now right now we have 4. I'm just going to erase all this so that we can continue. We've done QR and QP. So now let's do QS. So QS, their S is connected to T and P, so there will again be 2 Q S Q S. Sorry, Q. There will be 2 that start with QS. One will go to T, and one will go to P. That goes to P will have to go to R. Sorry, this one. And the one that goes to T will have to go to R as well. So it's just still connected. And now after it goes to R, now here's the difference. If it already came from P, then it goes to T and then Q. But if it started at T, then it'll go to P and then Q. So now we have the 2 that start with S that go QS. So that's 6. We've done the QP, QR, and QS. Now there's just one more vertex remaining, QT. So QT can either go to R or go to S. And then we just have to write both possibilities. And then if it goes to S, then it has to go to P, and then R, and then Q. And then if it goes to R, then it still goes to P, except now it'll go to S since it's already been to R, so now then it returns to Q. So our total is 8. And remember, you have to read the question. It's not asking for the Hamiltonian circuits, it's asking for the amount, so the answer is 8. So this is our question. In the undirected graph shown below, how many cycles are there? Remember that cycles must include at least 3 vertices in an undirected graph, and it is a different cycle if it goes the opposite way. So we can do this in a couple of ways. So first of all, we can go by length. So length 3 is the shortest that you can do. So there's W, Y, X, W. So it goes W, Y to X, back to W. And then this will be X2. This will be multiplied by 2 because it can go the opposite way. So this is 2. And then there's no others of length 3 that start with W. So we can start with X, X, Z, Y, X. X, Z, Y, X is another 2. So you add another 2 here. So now we have 4, and there's no others of length 3. So we have 4 now, and now we need to think of longer ones. And you cannot repeat the same edges. So here's one. You can go Z to Y, and then back to W, and then to X, back to Z. Remember, after going Z to Y, you cannot go back to X because you need to use this edge from Z to X to get back because you've already done this edge, and you will not be able to go to W and come back without repeating an edge. So Z, Y, X, Z is 2 more because it can go the opposite way as well. And before we had 4, now there's another 2, so now we're at 6, and there is no more because those are you can check, those are still the same ones, just they will be in a different order. So our answer is 6. And now let's move on to another question. Last question. Identify the starting and ending vertices that must be used in order to traverse the following graph. If it is not possible, write none. So we don't even need to find the traversal in this question. We are just being asked the starting and ending vertices. To find those, if you remember at the beginning of the video, we need to look at the degrees of each vertex, and if there is 0 or 2 odd vertices, then we can, if there's 0, then we can start from any, but if there's 2, it has to start from one and end from the other. So all we have to do is just figure out which ones are odd, and just look at the degrees of each one. C has 3, D has 2, E also has 2, so we can just keep doing this for every single one. Just make sure you know which degrees are for which ones so that you do not get confused. It's a pretty simple question overall. And now we're done. So you can see that C and G both have 3, which is an odd number. So, and those are the only 2 odd ones. So that means that's our answer, C and G, since it's not asking us for the traversal. It is just asking us for the starting and ending vertices. So that is the answer. So that's all for now. Hope you liked the video, and if you enjoyed it, please like and subscribe. So keep practicing, and goodbye for now.